Geometrical isomerism in alkenes, also known as cis-trans isomerism. Geometrical isomerism is a type of stereoisomerism. Stereoisomerism arises due to the different arrangement of atoms or groups in space. That means isomers have same structure, same formula, but different spatial arrangement. Arrangement of atoms or groups in space will be different. Geometrical isomerism is due to the different arrangement of atoms or groups around the carbon-carbon double bond. So here the isomers will be different in the way the atoms or groups are arranged around the carbon-carbon double bond. Let's take an example of an alkene of the type. Alkenes, we know there would be a carbon-carbon double bond. Let the groups attached to the doubly bonded carbon atom denoted by X and Y. X and Y are the groups attached to the first carbon. Similar groups attached to the second double bonded carbon atom also. That is X and Y. So consider an alkene of the type CXY double bonded to CXY. Here you can see X atoms are identical on both the carbon, both the doubly bonded carbon, and Y atoms are also same group attached to the doubly bonded carbon. This compound, this alkene can show cis-trans isomerism or geometrical isomerism. Let's see how different possible arrangement around the carbon-carbon double bond in space. If on the first doubly bonded carbon atom, if I am putting X atoms above, Y atom below, like this. Now on the second double bonded carbon atom, if I am arranging X atoms on the same side of here and Y atoms below. Here you can see the identical groups. X atoms are on the same side of double bond, above the double bond. Y atoms are below the double bond. Means identical groups or lie on the same side of double bond. This is one type of arrangement. This isomer is called cis isomer. In cis isomer, identical groups on same side of the double bond. Same side of carbon-carbon double bond. Now what is the second possible way of arranging these groups around the carbon-carbon double bond? See, in the first double bonded carbon atom, I am putting X above, Y below. On the second double bonded carbon atom, I am putting Y above, X below. See the difference in the arrangement. Here you can see X atoms are opposite side, above and below the double bond. Y atoms are also above and below. Means identical groups are on the opposite side of carbon-carbon double bond. So this is a different arrangement. This isomer is called trans isomer. What is the meaning trans isomer? Here the identical groups are on the opposite side of double bond. The isomers, geometrical isomers are called cis isomer and trans isomer. That's why the name cis-trans isomerism. So here the isomers differ in the arrangement of groups around the carbon-carbon double bond. Spatial arrangement of groups around the carbon-carbon double bond is different. In cis isomer, identical groups are on the same side of the double bond. But in trans isomer, identical groups are on the opposite side of the double bond. Let's take another example of alkene. Here the alkene is of the type CXY and CXZ. See, X atoms are similar groups on both the doubly bonded carbon atom. The other group is different. Let's try to draw the different ways of arranging these groups around the carbon-carbon double bond. So in the first double bonded carbon atom, X above, Y below. In the second double bonded carbon atom also I arrange X atoms above, Z below. Here you can see with respect to these X atoms, these identical groups are on the same side, no? This is cis isomer. Identical groups on the same side of the double bond. Now trans arrangement is also possible. Here in the around the doubly bond carbon atom, on the first carbon atom X above, Y below. Second carbon atom, if X atoms arranged below and Z above. See, identical groups are on the opposite side of the double bond. Hence, this is trans isomer. And the cis-trans isomerism is also possible with if all the groups attached to this doubly bonded carbon atom are different. That is, alkene of the type CXY double bond CZW. See, all the groups attached to the doubly bonded carbon atoms are different. In this type of alkene also, a kind of geometrical isomerism is possible. Now let's take a specific example of an alkene which can show geometrical isomerism. Butene. But-2-ene. Let's draw the structure of but-2-ene first. But-2-ene means how many carbon atom? 4 carbon atom. But means there are 4 carbon atom. If you number the carbon atom 1, 2, 3, 4, 2-ene. Second carbon atom there is double bond. Second carbon atom is double bonded. Second and third carbon atoms are doubly bonded. Now if I put the number of hydrogen, CH3 single bond CH, double bond CH, CH3, right? So these are the doubly bonded carbon atom. So you have to check the groups attached to this doubly bonded carbon atom. Here one hydrogen, one methyl group. On the second double bonded carbon atom also one hydrogen, one methyl group. So cis-trans arrangement is possible. Let us draw the two ways of arranging these groups around the carbon-carbon double bond. See, the carbon-carbon double bond, the 2,3 carbon atom have written here, but-2-ene, the 2,3, the double bonded carbon atom. How to arrange the groups? On carbon number 2, it contains a methyl group and one hydrogen atom. If I put methyl group above, hydrogen below. Carbon number 3, the second doubly bonded carbon atom, also CH3 group above, hydrogen below. Means identical CH3 groups above the double bond, hydrogen atom below the double bond. In identical groups on the same side of double bond. So this is cis isomer. This is cis-but-2-ene. Now in the trans isomer, how to draw? First carbon atom CH3 above, hydrogen below. Second double bonded carbon atom, hydrogen above, CH3 below. Means identical groups are on the opposite side of the double bond. So this is trans but-2-ene. So these are geometrical isomers or cis-trans isomers of but-2-ene. And these isomers have same structure but different spatial arrangement of atoms or groups around the carbon-carbon double bond. Because of different spatial arrangement, their properties will be different. Properties like polarity, dipole moment, melting point, boiling point, solubility, etc. will be different. These are isomers, same formula, same structure, but they have different properties. See, if you take but-2-ene, cis-but-2-ene is polar in nature. But trans-but-2-ene is non-polar. Cis-but-2-ene, there is charge separation. And the dipole moment value is 0.33 dBi. But it is non-polar means dipole moment is equal to 0, almost 0 for trans-but-2-ene. We can explain with this structure. If you take cis-but-2-ene here, cis-but-2-ene, the carbon-carbon bond is non-polar. Carbon-hydrogen bond, there is very small electronegativity difference between hydrogen and carbon. So this bond is also non-polar. So the polarity is due to this double bonded carbon CH3 carbon bond. This carbon bond. Double bonded carbon, there is a single bonded carbon. This bond is polar. We know doubly bonded carbon atom, the hybridization is sp2, right? Singly bonded carbon atom, the hybridization is sp3. So which is more electronegative? sp2 carbon atom with more percentage of S character is more electronegative. Electronegativity of sp2 carbon atom is greater than that of sp3 carbon. Why? Because of percentage of s character. Percentage of s character is 33.33 percentage in the case of sp2. Here the percentage of s character is only 25%. Greater the s character, greater the electronegativity. So sp2 carbon atom is more electronegative than sp3 carbon. So the electron pair of this bond will be more towards this sp2 carbon atom. Hence this sp2 carbon atom will be partially negative and sp3 carbon will be partially positive. Means this bond is polar. And how to draw the bond dipole? Bond dipole can be drawn towards the negative end. Crossed arrow. I hope you remember how to represent the bond dipoles. Bond dipoles are represented by crossed arrow towards the negative pole. So this bond is polar. Bond dipole act downwards. Now here also CH bond is non-polar, but this CH3 bond, double bonded carbon, then singly bonded carbon atom. Here also there is electronegativity difference. That is, this is sp2 carbon, this is sp3 carbon. sp2 carbon atom is more electronegative. So electron pair will be lying more towards this doubly bonded carbon atom, making that carbon atom negative partially and the other carbon atom partially positive. And the bond dipole can be drawn by a crossed arrow towards the negative carbon. So here also the bond dipole act in the downward direction. So there would be net dipole moment in the downward direction. Net dipole moment of the cis butadiene is 0.33 dBi and the molecule is polar. Whereas in the case of trans-butadiene you can see here also there is a polar bond. CH3 bond is polar. If you show this carbon atom negative, CH3 carbon positive, the bond dipole can be shown towards the negative pole, that is negative carbon atom, by a crossed arrow. Here the bond dipole of this bond act downward direction. Now see the second polar bond. This bond is also polar. This carbon atom will be partially negative. CH3 carbon will be positive. The bond dipole can be drawn by drawing a crossed arrow towards the negative carbon atom. See, so this bond, the second bond, bond dipole act in the upward direction, right? The first one, the bond dipole act in the downward direction. These two bond dipole have equal magnitude, but they act in opposite direction. So what happens? They cancel each other. Bond dipoles of 2CCH3 bond cancel out each other. So net dipole moment equal to 0. Hence trans-butadiene is non-polar. But cis-butadiene is a polar compound. So the cis-trans isomerism make the properties of butadiene different. Its polarity is different. Cis-butene is polar, whereas trans-butene is non-polar because the dipole moments cancel each other because they act in opposite direction. Here both the bond dipoles act along the same direction, downward direction. So there is net dipole moment, hence polar. Now let us try to draw the cis-trans isomers of a few number of compounds. As it is given in our textbook in problem question 13.10 and 13.11. Draw the cis-trans isomers of CHCl double bond CHCl. CHCl double bond CHCl. How to draw cis-trans isomers of this compound? We have the C double bond C. On the first doubly bonded carbon atom there are one hydrogen atom, chlorine. On the second carbon atom, if we arrange hydrogen on the same side, chlorine atoms on the same side, this will be cis. Trans isomer, how to draw? Hydrogen above, chlorine below on the first carbon. Second carbon atom, if you arrange them opposite. Chlorine above, hydrogen below. This is trans isomer. Cis isomer, trans isomer. Now, if we have given a compound, we should be able to identify whether cis-trans isomerism possible in the compound or not. Let us do one example. This is problem question 13.11. CH3 twice, C double bond, CH, C2H5. See, these two are the doubly bonded carbon atom. On the first double bond carbon atom, two groups are identical. CH3 group. Two CH3 groups are present on the same double bonded carbon atom. The second double bonded carbon atom, one hydrogen, one C2H5. Here, there is only one way of arranging these groups around the doubly bonded carbon atom. No, if you exchange the position also, we get a similar structure. That means cis-trans isomerism is not possible. Geometrical isomerism not possible in this compound, in this alkene, because two identical groups are attached to the same doubly bonded carbon atom. That group is not present on the other doubly bonded carbon. So cis-trans isomerism not possible. Let's take another example, CH2 double bond CBr2. So if you try to draw the structure of these compound, C double bond C, first carbon atom 2 hydrogen, second carbon atom 2 Br. There is only one way of arranging groups like this. If you exchange the position, there is no difference. There is only one possible way of arranging hydrogen and bromine, because two identical groups on the same carbon, two bromine atoms on the same carbon atom. There is no similar group on the adjacent doubly bonded carbon. So no cis-trans isomerism possible. Not possible. Cis-trans isomerism is not possible in this compound also. If you take another example, C6H5 CH double bond CH3. This is the compound. In this compound, if you try to draw different ways of arranging groups on either side of the doubly bonded carbon atom, doubly bonded carbon atom have written. One group is C6H5, the other one is hydrogen. C6H5 above, hydrogen below. On the second carbon atom, if I am arranging hydrogen below, CH3 group above. See, identical groups on the same side. One set of groups are identical on both the doubly bonded carbon atom. So this is cis. Trans structure also we can draw how? By arranging identical groups. That is, here the identical group is hydrogen. Hydrogen atoms on the opposite side. So with respect to hydrogen, the first one is cis. Here the hydrogen atoms are on the opposite side of double bond. Hence this is trans. With respect to hydrogen, the first one is cis isomer. This is trans isomer. In a similar way, one more example, CH3 CH double bond CCl CH3. See, let us try to draw the cis and trans isomer. Here, the first double bond carbon atom contain one methyl group, one hydrogen. Hydrogen above, methyl group below I have written. Then, second double bonded carbon atom contain one chlorine, one methyl group. Chlorine above, CH3 group below. See, identical groups. CH3 groups are identical on both the doubly bond carbon. So, this is cis. Identical groups on the same side. So, trans also we can draw hydrogen above, CH3 group below. In the second structure, if you put methyl group above, chlorine below. See, identical groups on the opposite side, hence trans isomer. Cis-trans isomerism is possible.